Aloha class, it's Friday. I got the orange shirt on. Just a minute, if you wear an Aloha shirt on an actual Friday, I'm going to hook you up with some candy. Make it an orange Aloha shirt, you're really going to hook up with candy. Now here we go. Chapter 2 is done. Hopefully you aced that first test. We start chapter 3 with our concept of derivatives, pretty much the entire first half of calculus. And we do it by defining derivative of a function and using derivative notation. Now, here we go. Our enduring understanding, learning objectives, and essential knowledge that we'll gain throughout this chapter. Learning objective, represent the derivative of a function as a limit of the difference quotient. So we bring our difference quotient with the idea of a limit, with thus forms this idea of what a derivative is. Here we go. Okay, so last chapter, we used a limit to find the slope of a tangent line. And what was crazy is without you even knowing it, you are finding the derivative all along. And kind of the most important thing we get here is the derivative is best thought of as a function that gives the slope of another function at any point. Remember, there's a couple things we want to remember with what we are about to do. Finding that limit of that slope of the tangent line is also finding the instantaneous rate of change at x. Or we also could say the slope of the tangent line at x. And those are very important things you want to remember going forward, okay? Now here's kind of our formal definition of a derivative. And we have two of them you want to be very cognizant of in terms of AP Calculus. And we have an original definition of a derivative, and you're going to find out in a little bit we have what we call the alternative definition of the derivative. Okay, this is our original right here. F prime of x is equal to the limit as x approaches 0 of our difference quotient, which is f of x plus h minus f of x all over h. Anywhere that the derivative exists, we say that the function is differentiable. Now, in AP Calculus, we're going to use a lot of different notation. Okay, if we're given, let's say, in a particular problem, y is equal to f of x. There's two types of notations that we like to use. One of them would be f prime of x. Another one we could say is y prime. Another one that's even a little bit more fancy would be dy over dx. And sometimes when we evaluate this dy over dx and we want to evaluate it or find the slope of the tangent line or find the instantaneous rate of change, and we want to find it at a specific value, we put this cool little bar and we write x is equal to, let's say, at the point A. Okay, and so that's kind of the notation we use a lot in AP Calculus. And you could see all of these on multiple choice questions throughout the AP, and you're going to see them all throughout the year in this class. Now, I'm going to erase things quickly, right? Mr. Graisley brought this up the other day in class. If for some reason you need a little bit more time to write something down, right? Because we're going to go kind of quickly here. Just make sure you hit rewind a couple times and hit that pause button. Okay, class, check these skills out now, okay? I think I got pretty cool and pretty good at this stuff. We'll see. Use the definition of the derivative, and we're going to use the original definition of the derivative to find f prime of x. Very first thing we want to do in this case is we are going to go f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now my guess is if you're in AP Calculus, this is pretty much good to go, so check this stuff out. I'm going to hit that dude and then that dude and booyah. Okay, there's all the math. Like I said, if you need to hit pause, you hit pause. Okay, we take a quiz or we take a test. I need your work to look like that. Okay, and the cool thing about this is what we are doing is we are finding the function for slopes of f of x. So as I do my math and I finish this bad boy, you know what's crazy? It means that the derivative is always equal to 3. And you know what's crazy if you think about it? We all know what this looks like. That's the graph of a line. And guess what the slope of that line is? That slope is that dude in front of that x. It's 3. It's 3 over 1, right? Up 3 over 1, up 3 over 1. And the tangent line is always 3. That's why we got a constant for our answer. And the slope at any single point on that bad boy is 3. Remember, hit pause if you need to write more down. Okay, here we go, our next one. F of x equals x to the third plus x squared. Now this is going to be a lot of work, okay? But first step, again, we're going to find the definition of the derivative using our original. So we're going to find f prime of x, which would be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now I highly encourage when you're doing a problem this crazy, okay, that has a lot of work in it, to do some side work. Okay, and you should do a little f of x plus h because I need to know what that is, right? And that's going to be x plus h to the third power plus x plus h squared. Oh no, how fun. That's a lot of work. And then you're also going to find out what f of x is. And then after you find those bad boys, you can go ahead and plug those back into your difference quotient, do some math, maybe do some factoring, who knows what, but you know what? This guy does. All right, there's your work right there. Okay, and yes, you should practice it. And yes, if you're feeling confident with this stuff, hey, you can go ahead and just take some quick notes. Remember what we should do right here, and you guys all know that's not my handwriting. We should have parentheses around that bad boy right there. And then guess what? This time I don't get a constant as my answer. Well, if I know what this graph looks like, it's a cubic graph, right? So it's going to have some different slopes all over the place. Ooh, no Bob Marley just yet, right? And so here we go. We have a little therefore. Okay, the derivative is 3x squared plus 2x. And guess what? That's going to give me the instantaneous rate of change. That's going to give me the slope of a tangent line at any point x equals a. So let's say I wanted to know, hey, what is the slope at x equals 1? All I have to do, and this is pretty awesome, I just put a 1 in for x and I do some math and check that out. It is 5. So if I were to go on this graph and I were going on to x equals 1, it wouldn't give me the y value. What it would give, though, is the slope of the tangent line, or more importantly, the instantaneous rate of change at x equals 1. Remember, hit your pause button if you need to write some of that down or take it in, or maybe even rewind a little bit. Okay, here we go. We have actually another definition of the derivative. It's actually called our alternate definition of the derivative. And what it is we just look at the instantaneous rate of change, or the slope of a tangent line, a little bit differently. Okay, now whenever we do slope, right, we always need a couple of points. So let's go ahead and make that guy c comma f of c, right? That'd be a little x comma y going on there. And let's make this point right here x comma f of x. And hopefully we all know by now that we want to find the slope, which any slope is your change in your y over your change in your x. So if I do a little rise over run, I get a little f of x minus f of c all over x minus c, right, class? That's the average rate of change. Now, how the heck am I going to turn an average rate of change into an instantaneous rate of change? Well, right, what I'm going to do is I've got a distance right here, x minus c. That's that distance. And guess what I'm going to do? I'm going to let this distance right here get closer and closer to 0. And when it gets closer and closer to 0, guess what? It's going to give me instantaneously what's going on. So in order to get this closer and closer to 0, guess what I'm going to do? I'm going to make x closer and closer to c. It's going to approach it. And thus, we come up with this really cool alternate definition of the derivative. And yes, you need to know both, which is f prime of c is equal to the limit as x approaches c of f of x minus f of c all over x minus c. Now this bad boy here takes some work, takes some major skills. So what I'm going to do is I'm not going to go bang, bang, choo-choo train on this guy and just give you the answer. We're going to actually do this together. Hey, I challenge you to hit a little pause button right now and see if you can do it on your own, and then repause and see if we get the same answer. Okay, I'm going to try to fit this bad boy in here. We'll see how it goes. All right, here we go. F prime of c is equal to the limit. This one is as x approaches c of f of x minus f of c all over x minus c. So I could do some side work, but this is pretty easy to get some substitution going on. I get the limit as x approaches c. F of x would be 1 over the square root of x minus f of c would be 1 over the square root of c all over x minus c. Whoa, that dude's a complex fraction. You know what we do with complex fractions. We find a common denominator or a lowest common denominator, and we multiply the top and the bottom by it to clear out our mini fractions. Now, when we do that, let's see what we get in the numerator. And it's going to help us out a little bit. But this guy's a little bit of a doozy. So if you were able to get this on your own, it just means you are amazing. Shame on me. There's no way when I multiply that by the square root of x times the square root of c do I get the square root of x, right? The x's would actually cancel themselves out, and I would end up with the square root of c minus the square root of x all over the square root of x, the square root of, c times the quantity x minus c. Now, what the heck? Shame on me. I should have plugged a c in there, and I would get 0 over 0. I could plug in a c here, and I would get 0 over 0. I could plug in a c there, and I get 0 over 0. What's that mean, class at home? Do something else. All right, here we go. What could I do something else here? Well, I have some radicals in the numerator, so that would probably suggest conjugates. The limit as x approaches c of the square root of c minus the square root of x all over the square root of x, square root of c times the quantity x minus c. All right, let's do this little conjugate thing. Conjugate, right, is so awesome because I don't have to do that whole FOIL stuff, and all I have to actually do is multiply the 2 first, 2 last. We can skip that inside and outside, right, you guys? Because those guys would cancel themselves out, and I get c minus x all over. What the heck? This is some crazy stuff in the bottom. X minus c, and I have a square root of x plus a square root of c. What is going on? Oh my gosh, if I plug in a c, I get 0 over 0, but oh snap. Kind of looks like I can cancel something out there. But they're not exactly the same thing. So what am I going to do? I'm going to take a negative out of the numerator and then check out this cool stuff that happens. Oh no, my marker stopped. Come on. Don't leave me now. All right, equals. Oh my gosh, my marker stopped. I have to try to use this pen now to finish this on my screen. So I apologize. Right? I just said, oh my gosh, the limit as x approaches c. I've got to take that negative out of the top, which thus would make the x positive and the c negative. And you know what's so awesome about that? And I apologize right now, class. I'm going to try to fit this in here. I get the square root of x, the square root of c. This is not easy to use. Times the quantity x minus c. And then we're going to even go over here, the square root of x plus the square root of c. I'm so sorry, but you see those bad boys cross themselves out, and then I get a little equals the limit. Don't laugh too hard at home. As x approaches c, I get a -1 upstairs. On the downstairs, I get the square root of x, the square root of c. Those guys cancel themselves out, and I get the square root of x plus the square root of c. But what's so awesome now, and thank goodness, because hopefully I'll fix this, is I could plug in that little c now and for all the x's, and I get -1 over the square root of c times the square root of c is c, and then a square root of c plus a square root of c is 2 square root c. And booyah! There you go. That is the slope of any tangent line on that graph, 1 over the square root of x. And obviously, I could simplify that a little bit. That's c to the first, and that's c to the 1/2, which would be -1 over 2 c to the 1 and 1/2, 3/2. Okay, and simplify that bad boy a little more. Once again, I apologize. Hopefully, I can get that fixed. If not, I'm cutting it off, and we'll keep the lesson going on the next video.